Hello, and welcome back to Introductory Electromancy. Today, we will be learning about your friend, the junction field effect transistor. I have taken a long time describing passive components before I finally got around to an active one. That is, a component that can switch another current or voltage based on an applied current or voltage. Everything up until now has been parts that do not do that have only two terminals, that react in some way to applied voltages or currents. Now I'm going to go opposite the usual order and demonstrate the junction field effect transistor before explaining how it works. And this is also the point where you find out why I named this Introductory Electromancy instead of electronics or electrical engineering, because it gets weird. Notice that this wire is insulated and the light is changing its brightness simply depending on how close I am to this wire. It would be very difficult to explain this to a peasant several hundred years ago without using terms like sorcery or magic, or in this case, I have decided to coin the term electromancy. So, this is an insulated wire. It should not be conducting a current, and also the brightness of the light varies from test to test. Now I am touching the actual conductive part of the wire. Sometimes the light is bright, sometimes it is dim, sometimes it is off. This is also an example of doing the same thing over and over and getting different results each time. Why? Why is this happening? Bright, off. So clearly I am producing some sort of signal, but the signal that is being detected in this case is not my own body's output signal. It's not from nerves or muscles. You'd use electromyography if you wanted to detect that. This is noise, mains hum, pollution, whatever you want to call it. This is because of all of the power-consuming devices around me producing an electromagnetic field that is then inducing a voltage in me because I am mostly water with some conductive salt ions in me. Let me see if I can get you a picture of it. Again, I'm doing this in the opposite order that I usually do. This is my oscilloscope. It is a real great scope. And I built it, 10 years ago, but from a kit. So don't get too excited, dear viewer. Let me now get a scope probe. I had tried to put off introducing things like oscilloscopes as late as possible in this video series because I want to emphasize that you can do most of this with very cheap components. You do not need a fully outfitted electronics lab with thousands of dollars in equipment in order to be able to do experiments and understand what the results are. So on one hand, I am simply going to touch the positive input of the oscilloscope and, hey, what is this sine wave? Behold, it is not there. Now it is there. Now it is still slightly there because I am holding this and a voltage is being induced in me, which is then through electrostatic effects like a capacitor inducing a voltage in this input lead. Now, this is for time adjust. It's probably easiest to see at 10 milliseconds per div. Oh, I saw the option. Sorry, I'm scrolling through menus on this oscilloscope. There we go. This is channel 1, channel on, increase gain. There we go. Now there's a nice sine wave. This sine wave is the result of power line, mains hum, noise, whatever you want to call it. Let me see if I can get it to show up properly. I touch it, and lo and behold, there is a 60 hertz sine wave. Now, if I were in Europe, I would get the same effect, but it would be a 50 hertz sine wave. And this is simply because of the mains frequency that is used in different regions. I believe everywhere in the world is either 50 or 60 hertz. The voltages are more varied, but not the frequencies used. It's because 50 or 60 hertz is about the right trade-off for making it so that your transformers are as small as possible, while at the same time losses from long power lines are as low as possible. And it's a balance between those two factors. But there's nothing. Now, if I touch the input lead, oh hey, there's a sine wave. That sine wave is from the electromagnetic field surrounding me as a result of our use of AC power, and it is being induced in my body and then picked up by this oscilloscope. The reason that is important is because it is this that is the reason that our little transistor circuit is behaving so strangely. Because depending on which point in the sine wave that I remove myself from it, the JFET, it takes an input voltage, and it allows a certain amount of current depending on how much voltage is applied. And I will explain why that is, but suffice it to say, I am releasing my finger at different instantaneous points of the cycle, which is being induced in me from all of the electrical wiring around me. And depending on where I stop in that cycle, it freezes the gate of the JFET at a particular voltage level, which corresponds to a particular amount of current flowing, which corresponds to a particular brightness. Very exciting, I know. So now I can actually explain why it is doing what it is doing, and also why you would see it light up when I am near it, and sometimes randomly be bright or dim or what have you. This camera is too slow to show that it is, in fact, when I do this, it's actually turning on and off 60 times a second. But you cannot see it because I am only shooting at 30 frames per second. Now, this thing, the JFET, the junction field effect transistor, what is it? What does it do? How does it work? What is its symbol? What circuit have I made here? These are a lot of good questions. Oh, and also, I should be able to turn it on and off on command. This should turn it off. And I see it only makes it dimmer. Now, if I cheat and actually plug the wire in like a real person, how does that work? I see. I do not have enough voltage available to fully turn it off. You will see why that is in the nearest future. This should turn it all the way on. This should turn it off. And it does not fully. I do not have enough available voltage to pinch off the channel. But in any case, off, on, off, on, off, on. All right. So, the junction field effect transistor, your new friend. No doubt who you wanted to learn about today. So, this tiny little transistor has a tiny little part number printed on it, if I can get my camera to focus. It might. Yes, MPF 102. A lot of electronics involves reading these little part numbers off of things and looking them up on the internet. So go to your happy internet terminal, whichever type you happen to be using. Type MPF 102. You may add the word datasheet in English or a variety of other languages. And then the result you want is something that will be a PDF file. Portable document format. So here is the top result. Different data sheets from different companies can tend to have different levels of quality. I've always been partial to National Semiconductor's data sheets, though they have since been purchased by Texas Instruments, so I don't know if they have been able to keep up their quality. Anyway, the datasheet for a part will tell you everything you need to know about it. Like, for example, this says it is obsolete. This device is obsolete. Please contact your on-semi representative for information. But there will be characteristic curves. There will be pretty, trippy-looking diagrams. And there is also everyone's favorite table, maximum ratings. Often this is called absolute maximum ratings, which makes it sound more exciting than it really is. Now let's draw a picture of a JFET. I'll draw the exact one that I'm using here, which is an NFET. So it flows really naturally from our description of the PN junction diode, except you add another lead. So you would get something like this. And then the schematic symbol for that will be this beautiful glyph here, which I am not drawing very well, but so it goes. It's going to bother me that that arrow is tilted because it actually indicates a different part, a unijunction transistor, which we can get into later, dear viewer. But a beautiful straight arrow, something like this. And then these are gate, drain, and source terminals. It's called the source terminal because it supplies electrons. These all get shuffled around if you have a P-channel junction field effect transistor instead of an N-channel junction field effect transistor. But examine the operation of the NFET initially. So we apply some voltage. And because this is just regular, old, boring N-type semiconductor, it has spare electrons that can flow, and current flows through the whole device. Conventional current flowing that way through the whole device. Now, this is great. It's not a particularly good conductor, but you can turn it on and off. And the reason for that is because of the depletion region, which we have already discussed, which forms whenever there is a PN junction. Now, you will recall from the previous episode on diodes that you can make that depletion region widen by applying a reverse voltage to the PN junction. And so if we have the same circuit, but we then apply a reverse voltage to the PN junction, so the P would be attached to the negative terminal for that to occur, then the depletion region widens. Widening that depletion region cuts off the available channel for conduction of current. And you can apply an even bigger voltage, and then what happens is you can completely cut off the channel. This is called cutoff or pinch off. In the datasheet it looks like it's called cutoff. So you apply enough voltage and it turns off the ability of this transistor to conduct. If you apply none, it conducts fine, and in between it will partially cut off but not fully cut off the channel. And so you can have a small voltage change here that produces a big change in the amount of current that is allowed through the transistor as a whole. Now, I mentioned that this is an NFET. This is as opposed to a PFET. Let me draw some little pictures. The NFET has an N-type semiconductor body, a little blob of P-type semiconductor, and the PFET is constructed physically the same but has the opposite going on. And so to turn off an NFET, you apply a negative voltage here, and it makes this depletion zone widen. However, the PFET, same deal, opposite polarity. Apply a positive voltage here, and your depletion zone widens until it cuts off the channel. These have lovely little symbols, frequently drawn with a circle surrounding them to indicate that they are discrete components. Not discrete as in hidden, but discrete as in individual, ETE instead of EET at the end of the word. So here you have your NFET and PFET, two glorious, happy types of junction field effect transistors. Really is bothering me that this diagram just isn't fancy enough, you know, dear viewer. It looks fancier to me. Not that it really matters that much. After all, we are just sort of stuck to a rock, hurtling around a continuous explosion. But there you go. So that is what is going on with this test circuit we have built here. Depending on what level of voltage is applied, it cuts off the conductive channel to a varying degree. When I remove my finger from the wire, the depletion region stays whatever size it was. Except for leakage currents, it should stay a consistent size because it acts as a capacitor that gets charged to whatever the applied input voltage is. Now, this beautiful data sheet tells me that the cutoff voltage is supposed to be minus 8 volts DC. And this is a 9 volt battery, so it should be sufficient to do that. It may be that my inductor experiments have finally brought it below a voltage of 8 volts, which is tragic, I know. So, we have described the JFET. I have shown you the MPF102 depletion mode JFET. I have shown its strange behavior. When we are allowed to physically play with it. How it reacts to my body having a voltage induced in it by the power lines that surround me. JFETs take very little current to turn on and off, which is why I can hold one end, the gate input, and then either touch the negative terminal of the battery to cause it to turn off, or the positive to make it turn on, and the current flowing through my body is sufficient to affect this change. Theoretically, a JFET has an input current of 0. In reality, it is leakage across this PN junction and between the leads through the air that will cause it to have a very tiny input current. But I think that more or less covers everything I wanted to talk about with JFETs. I picked this transistor to start with because it is, in my opinion, the easiest one to intuitively understand. That's all for today, dear viewer. Have fun out there.